Hello. This lecture we're going to have a review of some of the mathematics that we'll be using in the upcoming lectures in the course. We'll start with a review of algebra and statistics. We use mathematics in science, and there's several different goals of science. The three are description, prediction, and explanation. Description allows a description of various behaviors. Prediction supports reliable predictions from one variable to another, and explanation supports cause and effect explanations for why things happen. Descriptive methods include observational, case study, and survey methods. And predictive methods include correlational and quasi-experimental methods. When we question individuals on a topic and then describe their responses, we're using the survey method. And when we conduct an in-depth study of one or more individuals, we're using the case study method. The method that assesses the degree of relationship between two variables is the correlation method. And variables increasing or decreasing together is positive correlation, and variables moving in an opposite direction is a negative correlation. Explanatory methods include only really the experimental method, and it's used to identify the causes that determine when and why a behavior occurs, and involves using an explanation. A hypothesis is a prediction regarding the outcome of a study, and a theory is an organized system of assumptions and principles that attempts to explain certain phenomenon and how they are related. The scales of measurement include nominal, ordinal, interval, and ratio. The scale determines the amount of information contained in the data. This scale indicates the data summarization and statistical analyses that are most appropriate. Nominal data are labels or names used to identify an attribute of an element. It can be a non-numeric label or a numeric code. Example of nominal data would be students at a university are classified by the school in which they are enrolled using a non-numeric label such as business, humanities, education, and so on. Alternatively, a numeric code could be used for the school variable, 1 denoting business, 2 denoting humanities, 3 denoting education, and so on. Ordinal data have the properties of nominal data, and in addition, the order of or rank of the data is meaningful. Again, a non-numeric label or a numeric code can be used. An example here would be students at a university are classified by their class, and that class standing can use non-numeric labels such as freshman, sophomore, junior, or senior, and alternatively a numeric code could be used for the class standing as well, 1 denoting freshman, 2 sophomore, and so on. Interval data have the properties of ordinal data And in addition, the interval between observations is expressed in terms of a fixed unit of measure. Interval data are always numeric. An example might be that Melissa has an SAT score of 1985, while Kevin has an SAT score of 1880. Melissa scored then 105 points more than Kevin. Ratio data have all the properties of interval data, and in addition, the ratio of two values is meaningful. Variables such as distance, height, weight, and time use the ratio scale. This scale must contain a zero value that indicates that nothing exists for the variable at the 0 point. An example of ratio data might be that Melissa's college record shows 36 credit hours earned, while Kevin's record shows 72 credit hours earned. Then Kevin has twice as many credit hours earned as Melissa. There are 4 scales of measurement with these properties for each measurement. The nominal scale has the property of identity. The ordinal scale has the properties of identity and magnitude. The interval scale has the properties of identity, magnitude, and equal unit size. And the ratio scale has the properties of identity, magnitude, equal unit size, and a true zero. So let's provide an example of a variable measured on a nominal scale, ordinal scale, interval scale, and ratio scale. Gender and ethnicity would be variables for the nominal scale. Letter grade or class rank would be examples of variables in the ordinal scale. Fahrenheit temperature and SAT score would be examples of variables on the interval scale. And a percentage grade on an exam or your weight would be examples of the ratio scale. So a scale of measurement in which objects or individuals are categorized and the categories form a rank order along a continuum is the ordinal scale. A property of measurement in which objects that are different receive different values is identity. A property of measurement in which the ordering of numbers reflects the ordering of the variable is magnitude. A property of measurement in which a difference of 1 is the same amount throughout the entire scale is equal unit size. A property of measurement in which assigning a score of 0 indicates an absence of the variable being measured is absolute 0. Again, class rank is an example of the ordinal scale of measurement, and weight is an example of the ratio scale of measurement. An event or behavior that has at least 2 values is a variable. Data can be further classified as being categorical or quantitative. The statistical analysis that is appropriate depends on whether the data for the variable is categorical or quantitative. In general, there's more alternatives for mathematical and statistical analysis when the data are quantitative. Labels or names are used to identify an attribute of each element. Categorical data is often referred to as qualitative data, and it can use either the nominal or ordinal scale of measurement. So it can be either numeric or non-numeric. Appropriate mathematical analyses and statistical analyses are somewhat limited. A quantitative data indicate how much or how many. It's called discrete if we're measuring how many, and continuous if measuring how much. Quantitative data are always numeric. Ordinary arithmetic operations are meaningful for quantitative data. The manipulated variable in a study is the independent variable, and the variable measured in a study is the dependent variable. The group of subjects that serve as a baseline in a study is the control group, and the group of subjects that receives some level of treatment is the experimental group. A categorical variable for which each value represents a discrete category is a qualitative variable. A variable for which the scores represent a change in quantity is a quantitative variable. Statistics is the organized approach to collecting, analyzing, presenting, and interpreting data. It has applications in information systems, production control, accounting, marketing, economics, and finance. The term statistics can refer to numerical facts such as averages, medians, percents, and index numbers that help us understand a variety of business and economic situations. Statistics can also refer to the art and science of collecting, analyzing, presenting, and interpreting data. Some of the applications for statistics: public accounting firms use statistical sampling procedures when conducting audits for their clients. Economists use statistical information in making forecasts about the future of the economy or some aspect of it. Financial advisors use price-earnings ratios and dividend yields to guide their investment advice. In marketing, electronic point-of-sale scanners at retail checkout counters are used to collect data for a variety of marketing research applications. Production and manufacturing, a variety of statistical quality control charts are used to monitor the output of a production process. In information systems, a variety of statistical information helps administrators assess the performance of computer networks. Let's go over some terminology. Data are the facts and figures collected, analyzed, and summarized for presentation and interpretation. All the data collected in a particular study are referred to as the data set for the study. Elements are the entities on which the data are collected, and a variable is a characteristic of interest for the elements. The set of measurements obtained for a particular element is called an observation. A data set with n elements contains n observations. The total number of data values in a complete data set is the number of elements multiplied by the number of variables. A frequency distribution is a tabular summary of data showing the number or frequency of observations in each of several non-overlapping categories or classes. The objective is to provide insights about the data that cannot be quickly obtained by looking only at the original data. Cumulative frequency distributions show the number of items with values less than or equal to the upper limit of each class. A cumulative frequency distribution shows the proportion of items less than or equal to the upper limit of each class. And a cumulative percent frequency distribution shows the percentage of items with values less than or equal to the upper limit of each class. A table in which all of the scores are listed along with the frequency with which each occurs is a frequency distribution. A table in which the scores are grouped into intervals and listed along with the frequency scores in each interval is a class interval frequency distribution. Grouping the scores into intervals represents a class interval frequency distribution, and listing the frequency of every score represents a frequency distribution. Graphs. A bar chart is a graphical display for depicting qualitative data. On one axis, usually the horizontal axis, we specify the labels that are used for each of the classes. A frequency, relative frequency, or percent frequency scale can be used for the other axis, usually the vertical axis. Using a bar with a fixed width, we draw above each class label. We can extend the height appropriately to the correct count. The bars are separated from each other to emphasize the fact that each class is a separate category. A histogram is another common graphical display of quantitative data. The variable of interest is placed on the horizontal axis, and a rectangle is drawn above each class interval with its height corresponding to the interval's frequency, relative frequency, or percent frequency. Unlike a bar graph, a histogram has no natural separations between the rectangles of adjacent classes. A bar graph is used when the data are nominal and qualitative, and a histogram is used when the data are ordinal, interval, or ratio. There are several measures of location. Mean, median, mode are some of the more common ones, but we also have weighted mean and geometric mean. The mean is perhaps the most important measure of location. The mean provides a measure of central location. The mean of a data set is the average of all the data values. The sample mean is often used as a point estimator for a population mean. The median of a data set is the value in the middle when the data items are arranged in ascending order. Whenever a data set has extreme values, the median is the preferred measure of central location. The median is a measure of location most often reported for annual income and property value data. A few extremely large incomes or property values can inflate the mean, and that's why the median is used instead. The mode of a data set is the value that occurs with the greatest frequency. The greatest frequency can occur at 2 or more different values. If the data have exactly 2 modes, the data are bimodal. If the data have more than 2 modes, the data are multimodal. A number that characterizes the middleness of an entire distribution is a measure of central tendency. The mean is calculated by summing all of the numbers in a distribution and dividing by the total number of scores. Here we see some measures of variation. The range is the difference between the highest and lowest scores in the distribution. The average deviation is the average distance of all scores from the mean of the distribution, and the standard deviation is the square root of the average squared deviation from the mean of the distribution. Shapes are important as well. So again, in addition to the variability of a distribution of numbers, it's important to know about the shape of that distribution. Is it symmetric? Is it tall, thin, or is it flat? Based on these characteristics, we can mathematically do things with a distribution. An important measure of the shape of a distribution or set of values is called skewness. This in effect measures how lopsided a distribution is to the left or to the right. We can have an unskewed distribution, and you may have heard a distribution called the normal distribution, and that's unskewed. And in an unskewed distribution, the mean and the median are equal. We can also have a distribution skewed to the right or left. When skewness is negative, the mean will usually be less than the median, and when the skewness is negative, the distribution or the data set of values will be lopsided to the right, and the tail will point to the left. When the skewness is positive, the mean will usually be more than the median, and it will be lopsided to the left instead of to the right, and the tail points to the right instead of to the left. Kurtosis is a measure of how tall or how flat a distribution is. Mesokurtic is a median height and moderate breadth. Leptokurtic are tall and thin, and platykurtic are short and broad. It's often desirable to consider measures of variability or dispersion, as well as measures of location. And so, for example, in choosing a supplier A or supplier B, we might consider not only the average delivery time of each, but also the variability in delivery time. Even if they both deliver things in 1 week, if one vendor delivers thing in 6 days and then another time 8 days, giving you an average of 1 week, that might be preferred over someone who delivers something in 1 day and then the next time they deliver it in 20 days. And of course, standard deviation, as we mentioned, is a measure of this variability. And it's calculated by taking the average of the difference between all the scores in the distribution and the average of that distribution. And the standard deviation of a data set, again, is the average square root of the differences squared, is another way of putting it. A normal distribution is a theoretical frequency distribution having special characteristics. It has a mean of 0 and a standard deviation of 1, and the mean, median, and mode of the distribution are all zeros. And here we see the curve of a normal distribution. And of course this is a symmetric curve, and we see that the average, or mu, is located in the center. You have an equal number of occurrences in your data set below the average and an equal number above. And then it also has the properties that when we go 1, 2, and 3 standard deviations below, or 1, 2, and 3 standard deviations above, we get a symmetrically increasing or symmetrically decreasing frequency count in our data set. Typically we'll use tables to find the areas, or in other words the percentages or proportions of elements between various values in our curve. And again, this is a normal curve. It's known as a normal distribution or a standard normal distribution. Let's discuss a little about probability as well. So in statistics, the notion of an experiment differs somewhat from that of an experiment in the physical sciences. In statistical experiments, probability determines outcomes. Even though the experiment is repeated in exactly the same way, an entirely different outcome may occur. For this reason, statistical experiments are sometimes called random experiments. An experiment is any process that generates well-defined outcomes. And the sample space for an experiment is the set of all experimental outcomes. An experimental outcome is also called a sample point. So some examples of an experiment might be tossing a coin, and the experimental outcomes would be head or tail. Another example of an experiment might be inspecting a part on a production line, and the experimental outcome could be defective or non-defective. Another experiment might be conducting a sales call, and the experimental outcomes are a purchase or no purchase. Probability is the numerical measure of the likelihood that an event will occur. Probability values are always assigned on a scale of 0 to 1. A probability near 0 indicates an event is quite unlikely to occur. A probability near 1 indicates an event is almost certain to occur. Basic requirements for assigning probabilities are that the probability assigned to each experimental outcome must be between 0 and 1 inclusively. Also, the sum of the probabilities for all experimental outcomes must equal 1. The multiplication law is really an AND condition. So if you want to know the probability of A occurring and B occurring, you multiply the probability of A occurring by the probability of B occurring. The addition law is an OR condition. In other words, either event A will occur or event B will occur, or both. To find out the probability of A or B occurring, you add the probability of A to the probability of B. Here we see a tree structure for indicating the outcomes of various probability experiments, statistical experiments, and probability outcomes. In this particular case, it's for tossing a coin, and we can see that on the first toss we have a 50% chance of getting a head and a 50% chance of getting a tail. Then for the second toss, for each one of those, we again have a 50% chance of getting a head and a 50% chance of getting a tail. So the outcome of the experiment is going to be, in the first case, if we follow the upper path from our start, we get a head and a head as our outcomes. And it has a probability of 0.25. We go next head-tail, we get a head-tail outcome. Probability again is 25%. Going down the bottom path, we get a tail-head, and that means we have again a 25%. Probability, tail-tail, the outcome is TT, again a 25% probability. The sum of all probabilities of all our outcomes is 1, or 100%. If we want to find either all heads or all tails, here's all heads, 25%, or all tails, 25%. So we get a 50% chance, if we flip a coin 2 times, of getting all heads or all tails. Here again we see the normal probability distribution. Some of its characteristics are 68% of the values of a normal distribution are within plus or minus 1 standard deviation of its mean. So mu indicates the mean and sigma indicates the standard deviation. 95% of values in a normal distribution are within 2 standard deviations of the mean, from here to here. And then finally, 99% of the values of a normal distribution are within 3 standard deviations of the mean. So from minus 3 standard deviations to plus 3 standard deviations. The area under a graph and probability are identical. This is valid for all continuous random variables. The probability that x takes on a value between some lower value and some higher value can be found by computing the area under the graph of a standard normal distribution over that particular area. So here, for example, we find that the shaded area represents a probability that is less than 0.25, and the unshaded area represents a value of 75% that it's greater than this value k equals 1.66 in this example. Hypothesis testing can be used to determine whether a statement about the value of a population parameter should or should not be rejected. The null hypothesis, denoted by H0, is a tentative assumption about a population parameter. The alternative hypothesis, denoted by HA, is the opposite of what is stated in the null hypothesis. The hypothesis testing procedure uses data from a sample to test the two competing statements indicated by H0 or HA. So as some examples of an alternative hypothesis, many applications of hypothesis testing involve an attempt to gather evidence in support of a research hypothesis. In such a case, it's best to begin with an alternative hypothesis and make it the conclusion that the researcher hopes to support. The conclusion that the research hypothesis is true is proved or made, not necessarily proved, but is supported if the sampled data provides sufficient evidence to show that the null hypothesis can be rejected. So, let's take a few examples. A new teaching method is developed that is believed to be better than the current method. The alternative hypothesis is the new teaching method is better. The null hypothesis is the new method is no better than the old method. So you would have you would take a group of students using the old method and get their scores on a standard exam, and then likewise get students who have been taught under the new method and get their scores and compare them. A new Salesforce bonus plan is being developed in an attempt to increase sales might be another example. The alternative hypothesis is the new bonus plan will increase sales, and the null hypothesis is the new bonus plan does not increase sales. Another example is a new drug is developed with the goal of lowering blood pressure more than the existing drug. The alternative hypothesis is the new drug lowers blood pressure more than the existing drug, and the null hypothesis is the new drug does not lower blood pressure more. So you would take the existing reduction in blood pressure from the existing drug, then you would get some people with high blood pressure and give them the new drug and measure their blood pressure reduction. If it's greater than the old, you may have support for the alternative hypothesis. A one or two-tailed test is another important concept. The equality part of hypotheses always appears in the null hypothesis. In general, a hypothesis test about the value of a population mean has to take one of three forms. Either the alternative hypothesis is that the original mean is less than the new mean, or it can be that the original mean is greater than the or the new mean is greater than the original mean. So both of those are one-tailed test. When the new mean is less than the old mean, that's a one-tailed test. Or when the new mean is greater than the old mean, that's also a one-tailed test, because you're predicting the direction. The alternative hypothesis for a two-tailed test is you're not predicting a direction. You're not saying it's greater or less. You're just saying that the old mean will be different than the new mean. And you have to find out what direction it is. And in that case, you are conducting a two-tailed test. Because hypothesis tests are based on sample data, we have to allow for the possibility of errors. A type 1 error is rejecting the the null hypothesis when it's true. And the probability of making a type 1 error when the null hypothesis is true is called the level of significance. Applications of hypothesis testing that only control the type 1 error are called significance tests. The rule of thumb is that the type 1 error, you should not reject the null, but you do reject the null. So that's an error in that case. A type 2 error is accepting the null hypothesis when it's false. It's difficult to control for the probability of making a type 2 error. Statisticians avoid the risk of making a type 2 error by using the do not reject the null hypothesis and not accepting the null hypothesis. So they're never saying they accept the null hypothesis, they just say there's not enough evidence to reject the null hypothesis. So the rule of thumb here is a type 2 error is you should reject the null, but do not. And here we see a table with a action that's being done, what the null hypothesis is actually, and what the researcher concludes on the basis of their study. And you can see that in case of a type 1 error, the null hypothesis is actually true, but the researcher rejects it. With a type 2 error, the null hypothesis is false, but the researcher did not reject it. And here we see again area as a measure of probability. And more cases with some two-tailed tests where we are not predicting if it's greater than or less than, but we've got the possibility that it's both. We're going to find out, so we go into the experiment with the possibility that it's either. A conditional probability is our last subject for this lecture, and it's the probability of an event given that another event has occurred. So the conditional probability of A given B is denoted by the notation P and then in parentheses A pipe symbol B and then close parentheses. Here we see an example of one of the typical applications of conditional probability in spam filters. This one in particular is a naive Bayes spam filter. And as an example, we might say, what is the probability of an email being spam if it contains the word Viagra in it? So the conditional probability then would be P, the probability that it is spam, given that we have Viagra. And it just so happens that that's equal to the probability that it's Viagra, that we have the word Viagra, given that it's a spam email, divided by the probability that an email has Viagra in it when it's spam, plus the probability that an email has Viagra in it when it's not spam. And we can see down here, just as an example, if 50% of spam emails contain the word Viagra, but only 1% of non-spam emails contain it, then we can calculate the conditional probability with this by applying that formula to these values, and we get 98% of messages with Viagra are spam. All right, thank you. This concludes our review of mathematics for the upcoming section of the course.